Okay, I don't think I gave you an assignment, did I? Okay, so let's just get into, I want to do an outline of where we are so far. I try to add new little things, ways of looking at these outlines each time I do it. So this time I'm going to start with the 10 main things that I think like should kind of always be on your radar, no matter what topic you're in, no matter what the problem looks like. These are the 10 things to ask yourself, like, could this help me here? Okay. So 10 things that can help. Um, well, let me say that could help. They won't always, but um, in any kind of problem. Um, okay, so the first one is um, if the problem is a cycle. So, well, it doesn't matter if it's a cycle if the two states you're looking at are not at the ending points of the cycle. But if it's a cycle, a complete cycle from your first state to your end state that you're analyzing, um, then the change in any property is equal to zero. So Q is any property. Um, so that means delta U is zero. Um, delta P is zero. I'm not going to list all the properties, am I? Delta T is zero. Delta H and delta S. Let's just go with those. Okay. So whatever kind of property you're doing, if you have a cycle, there's no change from state one to state two. Related to that um, is steady state. And steady state says, we'll think of it as two things. The first one is that the rate of change of any property is equal to zero. So Q can be any property. And then second, the mass flow rate thing says MI dot is equal to ME dot. So this is if you're talking about control volumes, and it's equal to just M dot. So this is if you're doing any kind of control volume analysis. Um, third, so third and fourth are going to be the two main assumptions about materials that we make in this class. Third is going to be incompressible. Fourth is going to be ideal gas. So incompressible, if you have an incompressible material. Um, so we always use those for liquids. We sometimes use them for solids too, although solids aren't a very big thing in this class. You can think of the definition of incompressible is that the specific volume is constant. I didn't put that in my list of properties here, but that's also a property, by the way. And the specific volume being constant is the same as saying the density is constant. So either one of these are true. So if you take a cubic inch of water at the surface of the ocean and measure its mass, and then you go down to the deepest part of the ocean, yes, and measure the mass of a cubic inch of water down there, those masses are the same. They vary a little bit. Mostly they vary by temperature, but they don't vary very much by temperature, and they vary even less by pressure.
Part of my mom said that it was about, we were talking about paddles, I just said they were longer because the water was denser in the part of the
Oh, yeah.
surface because of the temperature.
Yeah, did you tell him he's a filthy, stinking liar? Yeah.
About it.
I mean, there is a pretty big temperature difference, but it just doesn't change very much by temperature. So the pressure, many thousand times pressure increase as you go to the bottom of the ocean, but the density doesn't change much at all. Okay, second one. The specific internal energy is a function only of temperature. Third, I'm gonna put this in a few different ways, but I'm gonna say CV and CP are equal to each other, and we'll just call it C. And the definition of C is the total derivative of specific internal energy with respect to temperature. And really, for the most part, the way that we're going to use this, the way we have used it and will continue to, is that the change in specific internal energy is equal to C times the change in temperature. And then the last one is that the change in specific entropy is equal to C times the natural log of the later temperature over the earlier temperature. And these two things, well, I mean, really all of this, but these two are the specific ones where it's important to notice this. You can use these for any temperature range. Anyone remember where this delta S expression comes from? Where did we derive that from?
Was it the second law of thermodynamics?
It was from the TDS equations, which are going to come up here in this list a little later on. Okay, and so this expression for delta S came from the TDS equations, and the expression for delta S for ideal gases also came from the TDS equations. Those things are so useful. Okay, any questions about incompressible materials? Anytime you see a problem that's liquid over the whole process, or especially if it says specifically that it's incompressible, think about using these, okay? Fourth is the ideal gas assumption. And we have a few more things that we know about ideal gases. It gets a little hard to remember all these, but the first one is the ideal gas law. And in our class, we do that as P times specific volume is equal to RT, and that R, remember, is for a particular gas. That's not the universal gas constant. Second, the same as the second one for incompressible materials, we assume that the specific internal energy is only a function of temperature. Third, enthalpy is only a function of temperature. And you can write that as, so remember the definition of specific enthalpy is U plus PV. Okay, little u plus p, little v. And PV from the ideal gas law is equal to RT. So we can write this as U plus RT. And so if that U is only a function of temperature, you can see why H is only a function of temperature. And then as a consequence of this, so this D comes from C, CV is equal to DUD temperature. And if you rearrange this and integrate, you can write that delta U is equal to CV delta T. And this is valid for, let's say, smallish delta T. So it looks a lot like the expression we have for incompressible materials. Instead of being just that that specific heat C, it's the specific heat CV. Otherwise, it looks the same, but this one is going to get less accurate as that temperature range gets bigger. Okay. We've seen it for a temperature range of 800 degrees Celsius or something, which feels like a pretty big temperature range, and it still gave okay results. It was off 10% or something. Okay, but anyone remember what is the reason that this becomes less accurate as delta T gets bigger?
Is CV the one that diverges or CP? I know
They both do.
Which one does it a lot though?
It's for ideal gases where it happens a lot. They both do it the same amount. I mean, and because we'll see that CP, is equal to CV. CV.
I thought you said that like one of them
plus R.
Like you can only do
Yeah.
for a small, and then one of them like 20 degrees is fine.
Oh no, both of them you can do for the same. I mean, they vary the exact same amount with temperature.
Oh.
But they just both, for an ideal gas, vary a lot more than C does for an incompressible material. So if you wanted to do it accurately for a big temperature range, you'd need to get that function CV or CP as a function of temperature. Yes?
The specific volume changes when it's an ideal gas, and that's why the specific heat gets less accurate for an ideal gas.
Let's see. I don't really have a good answer for why that is. But if you just look at a graph of any of these either of these specific heats as functions of temperature, you just see a big curve, and you see a very shallow curve for incompressible materials. And then what about CP? Well, CP is the total derivative of H with respect to temperature. And so if you use that expression from C, so this also comes from C, you get that this is equal to CV plus R. There are two more of these. The next one is more important than the last one I'm going to give. This is the one I'm going to usually want you to do on assignments and tests. But we have two expressions for delta S from the TDS equations. One from each TDS equation. The first one says Cp times the natural log of T2 over T1 minus R natural log of P2 over P1. And the second one says delta S is equal to CV times the natural log of T2 over T1 plus R times the natural log of V2 over V1. And you could solve one of these for natural log of T2 over T1. I guess solve both of them for natural log of T2 over T1, set them equal to each other to eliminate that and come up with a relationship between pressure and volume. Okay. These are valid for smallish delta T. And then the last one is if you have an ideal gas table, delta S is equal to S super 0 at T2 minus S super 0 at T1. Those are things you can look up in a table. Minus R times the natural log of P2 over P1. So this is using an ideal gas table for a specific gas. Which really means if you have a website or a table that doesn't bother to treat it as an ideal gas, you just have the website or the table for that material, you might as well just use that. But sometimes, like, you'll have a table that you don't have air in your table, but you have air as an ideal gas as a table. Okay, that's a lot for ideal gas. That's a lot to remember. Anybody have any questions about that? Mostly, I guess always if I ask for you to do it one way or the other, I'm going to ask you to use the expressions in D and E and F, and not to use the ideal gas table. Okay, so number 5, now we're out of ideal gases, is the work of expansion. this has been useful in problems from the start of the class, basically. W is equal to the integral from volume 1 to volume 2 of P d volume. One thing to be careful about this is that this is extensive volume. So if you have little v's, you're going to have to convert, or, you could rewrite this in terms of little v's. It just looks a little different.
That'd just be multiplying by
Yeah, so this would be, so it would be from mass times specific volume 1 to mass times specific volume 2, integral of P m d little v. What do you need in order to do this integral?
pressure as a function of
Yeah.
volume.
Exactly. So you need pressure as a function of volume. Or even better, if you're lucky, constant pressure. Question? Well, the nice thing about when P is constant, you can just pull it out of that integral. Remember, we basically have done this in two cases. One is where P is constant, and then we just pull that P out of the integral. It's super easy to do. And what you get is that the work of expansion is just equal to P times delta V. The other thing we've done is when we have those polytropic processes, then we have things to exponents, and you have to mess with the exponents, and it's a little more tedious. You have to figure out what the constant is and stuff. But if you just know the constant pressure the whole time, it's like an instant calculation. So I think still in all the problems that we do, if you see the polytropic expression or you see something saying it's a constant pressure, tell yourself, remind yourself to look for places to calculate that work of expansion. That's the most common way those things are used. Number 6, the mass flow rate. We mostly use this for control volume analysis, and it says that at any aperture, so at an inlet or an exit, m dot is equal to the area of the aperture times the speed of the fluid divided by the specific volume. So remember, this capital V is the fluid speed. And it's the average fluid speed, by the way.
Is there any way to differentiate between three different types of these? Volume, specific volume, speed?
I mean, I think the best thing for you to do, I mean, there would be ways to do it, but in the interest of making these equations look the way they're going to look when you see them next, I'd say just, you got to remember that. But we need a longer alphabet, that's for sure. We need more letters.
Great alphabet too, I guess, or are we already using some of those?
Yeah.
And then we could do like the AA and BB and all
Yeah,
that.
that's
That
true.
gets like a lot.
That's true. Okay, so number 7. Well, we don't use this too much in its full form. Mostly a lot of stuff that we use is derived from this, but this is the TDS equations. And the nice thing about well, let me write them down first. So TDS is equal to du plus pdv, and TDS is equal to dH minus vdp. And you might think, oh, like what magic can we unearth by setting these two equal to each other? And you just get a chain rule thing from the definition of enthalpy. It ends up pretty boring. But these are really useful. The main thing to remember about the TDS equations, or the main kind of superpower of the TDS equations, is that there are no restrictions on when you use this. Okay. So this is always applicable. I don't know what other things we have that where that's true, but it's true for this. So you don't have to think like, okay, this is a liquid, then it changes to a gas, or like, what am I approximating this way or this? This just always works for any material states.
P and V are specific in this?
Yes.
TDS?
Yep. All of these are specific. Number 8. This is a pressure thing. But it doesn't hold for a lot of our stuff. It only holds for a fluid that's at rest and continuous, in contact. All of it's in contact with each other. So for a fluid at rest and continuous, the pressure at the lower height is equal to the pressure at the higher height plus the density of the fluid times the acceleration of gravity times the difference in height between the two. So this is how you can calculate the pressure at the lowest point of the ocean or whatever.
Does that work for gas?
It does work for gas, except not really in this form, I guess. Like there's a version of, oh my God, I'm dying today. There's a version of this that's like an integral definition that I didn't give you, and I'm not going to now because I don't have it written down. But you would have to, the problem is for a gas, you have to take advantage, you have to consider the fact that that density isn't constant as you go down. And that's why you have to do it as an integral that includes that density as you go down. Okay. Any other questions on that one? So this one, I mean, you got to be careful of these two things. This doesn't apply unless you're just talking about a static fluid that's all in contact with itself. The 9th, there's only 10 of them. We're getting there. So this is the vapor dome. And it looks like this. It really doesn't much matter what the axes are. You can think of it as like okay, so let's think of it as temperature and specific volume. And it looks something like this, where you have a compressed liquid over here. Inside here, you have a saturated mixture of liquid and vapor. And over here, you have a superheated vapor.
Professor?
Yeah.
And what is like, I remember asking you this question before,
Mhm.
but like, if it's above the saturated mixture,
Mm-hmm.
like,
Yeah,
that,
then you have a very high temperature and a very high pressure. So this is called the critical point. And if you get the temperature and the pressure that high, uh, you lose a differentiation between liquid and vapor. So it's called a supercritical fluid.
and is that like a vertical kind of like thing, or is it like this where it's like mostly compressed and then it becomes supercritical?
You just
Or we just don't know really?
so remember that like if you're looking at a single process, it goes like this, gets here, then it transitions, and then
Oh yeah.
you get something like this.
Okay.
And eventually, and the heights of these shapes vary by how much pressure it has.
Oh yeah.
Okay, and so if the pressure is high enough, you get up to that point where this shape misses the vapor dome completely. And in that case, yeah, this just has different properties than a liquid or a vapor.
Okay.
Are there any processes where getting something to the critical point is necessarily reusable?
Yes, that's a really good question. So there are power plants where, we're going to talk about power cycles and stuff, and you get more efficiency out of your power cycle from having higher pressures and higher temperatures at the boiler. And so you can get some good efficiency payoff by increasing the temperature and pressure that much. There are trade-offs too. A supercritical fluid causes a lot more damage to turbine blades and stuff. But apparently there are some power plants that use supercritical fluids, but it's more expensive. And inside the vapor dome, before I say that, let me say, for compressed liquids, and superheated vapors, you need two properties to look up the other ones. Inside the vapor dome, you only need one property.
And quality?
Yeah. So you need one property to look up the value for a saturated liquid and or the value for a saturated vapor. And if you want the total of your mix, your specific mix, then you need that quality. And then the quality is the last thing I wanted to give in this. And that is that inside the vapor dome, X times the property value for a saturated vapor plus the quantity 1 minus X times that property for a saturated liquid is equal to Q. So this is for any property Q. We haven't used this a ton of times yet, but we actually are going to in the next section. We're going to use it a lot. X is the quality, so at a single state, that is the fraction of the material that is a vapor. So if you're at a saturated mixture, it's the mass that's vapor divided by the total mass. So if you have completely a saturated liquid, then the quality is 0. And if you have a saturated vapor, the quality is 1. And if it's not in that saturated, if it's not inside the vapor dome, quality doesn't mean anything.
Professor, could you write down the quality equation, please?
The definition?
Yeah.
Yeah. So X. X is equal to the mass that's vapor divided by the total mass. Oh, I guess, I'm sorry. This was supposed to be my 10th. Just put a little number in front of that. I got carried away on number 9. So that's the whole list there. So those 10 things can get you out of trouble in a lot of cases where, like, I think you can think like in a problem, there's a certain amount of stuff that's just like, well, if you can identify that this is a problem where we're using the first law for control volumes, there's a certain set of steps. If you go through the steps and you get to a sticking point where you don't have what you need, very often the answer is in these 10 things. Okay? Any questions about those? All right, so now I'm going to do sort of a quick abbreviated outline of the course topics we've talked about so far. The first one is the first law of thermodynamics. And we did this in a couple different ways. The first one was for closed systems. Over a finite time interval. So what does a closed system mean? Yeah, that's right. You're looking at the same material the whole time. You have a blob of material and you're tracking all that same material over the whole time interval. And this says the change in E is equal to Q minus W. And pretty often in this class, delta E is just going to be equal to delta capital U. Then second, we did it for closed systems in a differential form. And so the equation itself says dE dt is equal to Q dot minus W dot. And similar to above, often dE dt is treated as d capital U dt. And then for the closed systems in differential form, we had a little side project when we were talking about this, which was heat transfer equations. So this, if you're given heat transfer, if you're doing calculations with heat transfer, you're almost always going to end up using this differential form because that's the form that we had for heat transfer equations. So the first one, is, well, let me say, first one is conduction. And so Q dot is equal to negative kappa times A times dt dx. And this is the form that you see, so I'm leaving that negative there, but remember that negative really doesn't mean anything for us. We're going to come up with a sign by inspection. Remember that none of these heat transfer equations, sign conventions, can be assumed to work with the first law. So you always have to think about the direction of heat flow. It's not hard. It's always just going to go from the high temperature to the low temperature, but you always have to think about that. Think about which one is your system. Yeah. So I'm with all of these heat transfer equations, the direction of heat flow is just going to be from the high temperature thing to the low temperature thing. Okay. So it's easy to figure out which direction heat is going to flow. But then you have to think about, remember that to use it with the first law, Q dot has to be positive if energy is going into your system. And so the sign depends on whether your system is the higher temperature thing that you're talking about or the lower temperature thing. Okay. So like if you think of heat in the winter leaving a house through the window, okay? Well, you know that heat is going to transfer from inside to outside, okay? That's all heat knows how to do. But whether that Q dot ends up being positive or negative depends on whether your system is inside the room, in which case Q dot would be negative, or outside the room, in which case Q dot would be positive. And also remember that for us, dt dx is always going to be, well, I should say temperature is always going to be linear with x. And so this is always just going to be the total change in temperature over the total thickness of the path. Next is radiation. This is the only one that transfers through empty space, and we have two for this. We have Q dot is equal to the emissivity times the universal Stefan-Boltzmann constant times the surface area of the object times the temperature to the fourth power. And if you're going to use this in the first law, you have to use a modified form of this that is, so it looks similar, emissivity, Stefan-Boltzmann constant, surface area times the quantity, temperature of the body to the fourth power, minus temperature of the surroundings to the fourth power. And this is for a smaller body surrounded by a larger body.
What about if it was like a really hot, larger body surrounding a smaller, colder body?
Yeah, it's the same. You just have to think about just the direction would be different. It's the same calculation. So that can be for heat dissipation or heat, bringing in heat. And then the last one is convection. And that equation is Q dot is equal to this catch-all constant times the area that's exposed to the fluid times the quantity temperature of the body minus temperature of the fluid. And again, it doesn't matter which one is hotter or colder. That just determines the direction of flow. What? That is a constant that comes from experiments. So that's just something that has to be given in problems. There's no way for you to like calculate that or anything. But it has to be very specific to your case, to the problem's case.
Temperature body minus temperature of fluid?
Fluid, yep. Okay, well, I'm not quite done with the first law, but let's stop there and we'll finish this next time.
Thanks, Professor.